Welcome to the lesson on strings and pulleys. So today's goal, I want you to be able to evaluate the forces acting on a system that involves strings and pulleys. Surprise, surprise there. So many real-world applications, they use strings and pulleys. So for example, we're talking about elevators, anything that involves a cable, so a winch system, block and tackle, etc., etc. So elevators, they're not simply suspended from cables. The cables are involved and pass through a series of pulleys to gain some mechanical advantage. So we are going to look at how to calculate some of the tension in some simple systems, and then you get the opportunity next year if you take a physics course to do some of the more complex. So when dealing with string and pulley questions, it's necessary to draw the free body diagram for each object being considered. So now we need to investigate the multiple objects that are in the system. So we're going to have multiple free body diagrams. The resulting acceleration of any system, it's determined by the unbalanced force. So that's just Newton's second law, so nothing new there. The unbalanced force can be determined by finding the difference between the force of tension in the rope and the force due to gravity. So that being said, let's talk about the strategy in order to solve systems that follow along with this or within this category. So what's our strategy? Well, number one, what we need to do is we need to determine direction of motion. Now, you're not always going to know the direction of motion. So there are times where you're going to have to take an educated guess. So you are guessing that it's going to move clockwise. All right. If it's not given, and more than likely it won't be, you're going to have to make that guess. Now, 9 times out of 10, you're going to be correct. The ones that are on the fence are the ones that are going to be a little frustrating because you got to go back and redo it if you're incorrect. Next, you calculate the acceleration for the system. Calculate the acceleration for the system. Acceleration for the system. So you look at the entire system as a whole, and you determine the acceleration of that entire system, and then you can calculate tension. Calculate tension using the acceleration. All right, so there are your 3 steps in the process for solving questions that involve tension. So let's take a look at a series of examples. So 0.7 kilogram mass is suspended from a cable. So let's call this object A. This one we'll call object B. Cable passes over a pulley and connects to a 1.5 kilogram cart. So that's object B. We're going to assume negligible friction. So that means we can ignore friction. Calculate the acceleration for the system. So our FBDs are free body diagrams. So I'm going to have object A, and I'm going to have object B. So object A, there's only 2 things that are really acting on it, and that is our force due to tension and the force due to gravity for object A, so FGA for my subscript. For number B, or for object B, we have a tension force moving to the right. We then have force due to gravity, FGB, and then we also have our normal force. So there are the 2 free body diagrams for this system. So direction of motion, this is where you take an educated guess. Since there's no friction, we can assume that that is the direction of our motion. I'm just going to put that in there for note purposes. So once we have that, the second one's to calculate acceleration for the system. So we know that our acceleration is your unbalanced force. So unbalanced force is equal to mass times acceleration. So what is involved with our unbalanced force? What is acting against the motion? And when we see that there's no friction, it's simply going to be it's going to be the mass of object A. So our unbalanced force is our FGA equals mass times acceleration. And you see that because the tensile force, if you look at object B up here, up here, okay, and then the corresponding in the free body diagram, there's nothing opposing motion. So that means the entire force being applied to B comes from your force due to gravity. So that's kind of your driving force. That being said, we know that the mass of the object is 0.7. Again, I'm just going to use 10 for gravity. Mass, and now this is mass of system, all right? So it's mass of system, so I'm going to put the 0.7 plus 1.5, so when you look back in the note, you can figure out where that comes from. So we end up with 7 equals 2.2a. So the acceleration for this system is the 7 divided by 2.2, sorry, and we find that we get 3.2 meters per second squared, and it's going to be down for A. All right, so there we go. Or we can say, actually, let's go clockwise just to follow along with the red arrow. So there's our acceleration, 3.2 meters per second squared clockwise. And that's all that was really required here, calculate the acceleration for the system. So therefore A is 3.2 meters per second squared clockwise. Okay. Moving along then, next example. Now the 0.7 kilogram mass is suspended from the cable, so it's the same question. However, we're looking for the smallest coefficient of static friction that will keep this system stationary. So really, I'm just going to go CFBD for previous example. So all that we're doing, we're really just using the previous question. It's like putting a B part to it. Oh, example. Try that again, example. The only thing that's really changed is object B. I'm just going to go back to that for a second. I'll reconstruct its free body diagram so that it's in front of me. Tension, normal. Now we have a frictional force. So we want to make sure that the system will remain stationary or will not move. So we know that in this case, the unbalanced force, Fu equals mass times acceleration. I know that my force due to gravity, or driving force, minus force due to friction, will have to equal 0. So now we can just continue on as I did before, because we want to find that mu. I'm just going to expand this out. So the driving force was the mass of object A multiplied by gravity. So mass of object A multiplied by gravity minus your friction, remember, is mu. The normal force, so it would be Fn. I guess I'll show all steps here since it's an example for you. Minus mu. Your normal force is mass of object B. Okay, that is what is causing that frictional force. All right, so right here, this is where friction is determined. It's from that interaction between object B and the surface. All right. That being said, got it all set up and expanded. You can see gravity actually divides out of the equation. And if I rearrange, mass A equals mu mass B. So mu, in this case, the relationship would be mass A over mass B, and then you can do the calculation. You can actually plug the numbers in whenever you feel comfortable. So 0.7 over, I believe it was 1.5. So we end up with 0.7 divided by 1.5, and I get 0.47. Therefore, mu s must be a minimum value of 0.47 to not move. Keep it simple here. Okay, so just really a B part to that initial question. Wasn't introducing a whole lot new, just taking a look that we can change the direction. Cables help us change the direction of applied forces. Now let's talk about something that's a little bit more to the point in today's note. So we're looking at finding the acceleration for the system and the tension in the rope. So starting with the free body diagrams. So FBD. So I'm going to call this one object A and the 30 kilogram object B, just to keep life simple here. All right, now this 20 kilogram mass, once you put it on a slope, things get a little bit more exciting here because I now have a tension force. I have an FGX, and that is for object A. So now the subscripts, you don't have to really do it that way with the subscripts, but I just prefer doing it myself. F of G for A, my normal force of A, so FNA. And there is friction, and you know there's friction because mu K are given for the different surfaces. So I'm going to hold off for a second, and I'm going to have a bit of a discussion here after I clean up the second diagram. So FGXB, FGB, my tension force, and FNB, so my normal force. Okay, the only other thing I haven't put in here is friction. I have not put friction into my equation at all. So I've done my free body diagrams. Now I've got to go back and look at this system. And this is an educated guess. You're asking yourself, which direction is this system going to go? I would say since this is a greater mass right here, and it's also on a steeper slope, I would anticipate that my system is going to go clockwise. So there is my motion, which means that, and I'll just change the color, for the 20 kilogram free body diagram, my force due to friction will be pointing in that direction for object A, and my force due to friction will be pointing in that direction for object B. So there we are. That is what the final free body diagrams look like. It's important that we have all of that information because, and I'm just going to shrink it down so I have a little space to work with here, because now I know the direction and motion for all my information. So I can go to my unbalanced formula, or FU formula. So I know that unbalanced force is mass times acceleration. So now when I looked at my unbalanced force, I know that the driving force is going to be clockwise. So what is my driving force? Well, that's it right there. That's the only arrow that's pointing in the direction to drive the force. So that means that F, the force due to gravity on object B, is driving this entire system. So what is working against it? Well, force due to friction from itself minus the force due to friction from object A minus the force due to gravity from object A. And that's going to be my mass total multiplied by my acceleration. So there we go. There is the balanced equation. Now you'll note T is not in this at all. Okay, if you take a look, I never use T. Okay, there's no tension force in that balanced force diagram. And the reason for that is that tension is not a driving force. It's not a resistive force. It's a force that connects the two objects together to form this system. So that's why it's not involved at this point. All right, so I'm going to finish this up in the next video so I don't have to rush through the algebra. I can talk about it a little bit as we go through it.